Hello, this is Dr. Christy Patton-Lukes, and this video is going to complete our lesson on batch processes. In particular, we're going to be looking at the scheduling for batch processes and using Gantt charts. Gantt charts are tables that represent tasks in each row over a period of time. These can be created in a spreadsheet, for instance, and you look at time and you see that if one job needs to be completed, the next one can't start until that time. And it runs like a timeline. For the process that we're looking at is the example from the previous video. So steps 1 and 2 take place in the reactor. I really need to just consider both of those at the same time because they're using the same piece of equipment. This is going to be really more about whether or not the equipment is occupied rather than whether the chemicals are occupied, although both matter, but this is about the equipment. And then we're going to send it to a filter, then our still, our crystallizer, our dryer, and our packaging plant. If your goal is to produce 5,000 kilograms, and we designed this step to only create 6,000 or 635 kilograms, then divide that out and you see that we're going to need to repeat this process 8 times. Now if you do all of this and you do it all the way through and it takes you 14.5 hours to make the complete batch, and then you start over at the beginning with the next one, 29 hours and you've only got 2 batches made and you've got to do 8. That's 116 hours. That's a long time. And in the meantime, your equipment is sitting unoccupied for much of this time. So we can overlap our operations. And we can slide this entire picture back until we finally get one of these diagrams that just touches. And in this particular case, our longest step becomes the problem here. This is our tray dryer, and if you look at that, these just barely touch. Everything else has some downtime in between, but we're able to go through and do all of these batches, and we can do all of our 8 batches in 42.5 hours, which is much better than the 118 we were looking at before. So compact scheduling can help us to process materials much more efficiently. And a tool we use for analyzing them is the Gantt chart. Now if you want to just do this computationally, you can make some estimates and compute cycle time. If you do it without doing overlaps, this is what NO stands for here, you take the time to do it without overlap for 1 cycle. Well, I got that wrong. Okay, this is for all of the cycles. To calculate for 1 cycle without overlaps, I then just take the total time and divide by n, which is the same as just finding the time for 1 cycle. Nothing very exciting there. But if I'm going to do it with overlaps, what I want to do is I want to look for what was that longest step. And here it was the tray dryer. And I'm going to add that up for n-1 of them and add that to what it takes to process 1. And that will actually correctly get me the total time for all of them. If I want to know the average time for processing, I just take this total amount of time and divide by the number of batches, and I can get a time for 1 cycle when I do the overlaps. If n is a large number, this approximately is equal to just the sum of the maximum total time for that longest step added up for all of my batches. And that is just an approximation, but it's, not too bad. So in this particular example, the cycle times were 14.5 hours if I didn't overlap, and I get roughly 4 hours with overlapping. So that's a big improvement. Now there are 2 different ways that you can run a batch processing plant, and they are called a Flowshop and a Jobshop. A Flowshop might produce a lot of different products using the same equipment in the same order, but you need the equipment or you need the materials in the equipment for different lengths of time. So maybe you're making chocolate chip cookies and sugar cookies, and it takes a little longer to mix the chocolate chip cookies. If you've ever made them, you would understand that. A job shop is going to produce different products that are going to require different equipment and use each piece of equipment in a different order. So that's going to be more complex scheduling. I'm not going to be able to, with a job shop, just use my simple little formula of saying, take the longest step and multiply by the number of batches I'm going to run. Now in the textbook, they look at an example and they look at 3 different processes that you can make A, B, or C. And each of them have a mixer, a reactor, a separator, and a packaging step. Okay, and the times for each one of these are shown here with the total time over here. We want equal number of these batches produced, like, for the next 6 years or something like that. We want to figure out how many batches can I produce? What's the most efficient way to run this? And how much can I make in 1 month of operation? And for our purposes here, we'll base this on a 500-hour month. Okay, that 500 hours is based on a 6,000-hour operating year, which is a 3-shift, 5 days a week. Anyway, so a 500-hour month is what we'll call it. If you look at this, I'm going to do the same number of batches for each of mine. For A, the longest step is 2.5 plus 8. This one is 4.5 plus 9.5. The rest of the time for the batch, so the total batch is here. And I can use this, set it equal to the 500 months, and that will get me an approximate value for X of 42. So I can make roughly 42 batches of each product. Okay? I can run this so that I make 42 batches of A, and then clean everything, 42 batches of B, clean everything, 42 batches of C, clean everything. But if I do that, the problem is that then I have to store the A, the B, the C eventually, until I'm ready to send it out to market. I can also run it as an ABC, ABC, so I just alternate all the time between the different products. And if you do this, sometimes you can see a savings. Not always, but sometimes. And so in this particular case, if you run A first and then B, the closest you can get is this shown here, and then C. And our limiting steps, well, the reactor and the separator both turn out to be equally limiting. And they both are in use at all times, but the packaging and the mixing step get some breaks. And if you do this for 42 batches, then you finish with some time left in the month. Okay? If you want to go for the entire 500 hours, you can run 47 batches. A job shop, the idea here is that for maybe A, I need to mix and then go to the separator, but I don't have to do any reaction, and then go to packaging. But B needs to mix, then go to reactor, then go to a separator, then packaging. C doesn't need to be mixed, it just needs to react, go to the separator, go to the packaging. And so scheduling these are just a little bit different. You can still do them using the Gantt chart technique. Draw an individual plot or plan for the A product, the B product, and the C product, and then see how closely you can smush them together to get an efficient work plan. And they go through and look at this example. You'll probably want to pause the video, maybe try this a little bit on your own before you move on and look at the answer. So here it is for if you just make 1 batch of each product. Okay, I can see that the separator really seems to be the delay point here. but the reactor isn't used for B, it is for C, so maybe if I kind of switch the orders here, and they go through and look at these. If you just do AAA, BBB, CCC, they can go through and look at the timelines for those. If you do these as ABC, this is the picture. And you also could have looked at ACB. Now, in this example, it's desired to produce the same number of batches of A, B, and C. Use the numbers from the last one and figure out how many batches of each product can be produced in a 500-hour month using a single product campaign and for a multi-product campaign. And here they're doing it analytically. And so just applying the equations that we had seen earlier, they estimate that 34 batches in a month for single product and 25 batches in a month for the multi-product. You would need to, as the engineer, balance the relative needs of being able to make more product, but having to add storage facilities. Now, they look at product and intermediate storage, and in this case, okay, if they were going to do this goes back to example 40 or 3.3, and if they did 43 batches, they would be able to make 10,000 kilograms per month of A, 15,000 of B, and 12,000 of C. And if you just assume that it's roughly the density of water, you can actually estimate what the volumes are that you're going to have for these, and then you know what your cycle times are. We've estimated those earlier. And so our production rate and then our demand rate, and balance those and see how much storage you actually are going to need. Storage capacity can be estimated by just using simple linear relationships. So the slope while you're producing, and the slope is while you're no longer producing that product, but just giving it out to customers. And if you had shipping schedules, you could, maybe do a little bit better job of this, but using some estimates that they give in the book, they come out with these equations here. And based on that, they find that they're going to need roughly an 8, 10, and 8 cubic meter storage vessel for each of these products. And sometimes as we're going through and doing this, we just simply need an intermediate storage between steps. Maybe I can run the reactor very efficiently, but the crystallizer is a little slow for one of my products. If I just had some storage, I could double up and put 2 batches of B, for instance, in together in the crystallizer and speed the whole process up. I would just simply need some storage. So they try to talk you through some creativity in doing some of these things when your rate limiting step, your longest step, for one product is very different than for a different product. And they show variations on that. For instance, if you put in 2 different crystallizers, that maybe you can make enough extra batches to pay for that extra crystallizer. In example 3.8, they look at yet another one of these, and I'm going to let you read through this on your own, pause it, take a moment to look at it, and see how you can do at estimating your size needed eventually for the reaction vessel. Here we have what they came up with as their answers. They did this for B and C. And again, I'm not going to spend the time reading through this. This is out of your textbook. And here is a practice problem. I always, when I'm doing this as an active classroom activity, I divide the class up and have each one do one of these campaigns, either the single product or the multi-product in B or the multi-product in C, and determine how many batches could be made in 500 hours, so I recommend that you take the time to try one of these also. And here are answers. And then they look at one where they have limited reactor size and some more data associated with that. Again, I want you to read these and take the time to work through these examples on your own. And here are the solutions to those. And this one, this is calculating that they come up with the 9.78 cubic meters is how much storage they needed.